Hey y'all, my name is Seth Adams. This is Lab 4 Circuits. Alright, so the purpose of this lab is to predict the behavior of circuits containing resistors in both parallel and series form. And to do that, we're going to use the voltmeter and the ammeter to measure the current and potential difference across the circuit. And we're going to examine behavior of the capacitors and resistors. For the main lab results, the node and loop rule were satisfied and RC is time dependent. For the principles that we used in this lab experiment, we used the loop rule, which is delta V round trip equals 0, the node rule, which says IN is equal to I out, and Ohm's law, which is V equals IR. So overview of the experiment. For our procedure, we're going to create both series and parallel circuits using the PHYS virtual circuit builder. We're going to measure the potential difference in current using the voltmeter and the ammeters, and then we're going to graph the result. For our initial conditions of the experiment, we start with two 1.5 volt batteries, a 47 ohm and 100 ohm resistor, and 2 ammeters. So in this experiment, we've got the system and the surroundings. The system in this case is the circuit, while the surrounder is everything else. So data-wise, for circuit 1, the current is 0.02 amps. If the ammeter was reversed, then the current shows negative current, where over here for circuit 2, the current is 0 amps and the voltmeter is putting off 3 volts. So continued measurements of voltage at the different segments. AB was equal to 3 volts, BC 0, CD is negative 0.96 volts, D is 0, EF is negative 2.04 volts, FG is 0 volts, GH is 0 volts, and HA is 0 volts. And you can look at what we got down here, where delta V equals 3V minus 0.96V minus 2.04V, so that you do get back to 0 and everything equals out. So for calculations, we're looking for R, which we solved that as V over I, and R of 47 ohms is 0.96 volts over 0.02 amps to give us 47 ohms. For the R of 100 ohms, you've got 2.04 volts divided by 0.02 amps to get back to your number 100. For the wire, there's 0 volts flowing through it and 0.02 amps, so you're still sitting at 0 ohms. And same thing for the ammeter. So the potential difference visually over here on this graph, wires have negligible potential difference, battery has a positive potential difference, and resistors have negative potential difference. As you can see over here with our markings of 3, 2.04, 1.5, and 0 down here. So the node rule, looking at it visually, the ammeter has negligible resistance. The current from the battery is split at the node. This is where the node rule comes in. The most current moves around the resistor. Right here. So for the RC circuit, the light bulb lights up immediately and then dims quickly. The capacitor is charged when the bulb is out. When we remove the battery, that causes the light bulb to light up because the capacitor is discharging. So time-wise in this circuit, 10 ohms took 8.2 seconds. 20 ohms took 19.7 for them to charge up. Discharge-wise, for the 10 ohms, it took 9.8 seconds, and for the 20 ohm resistor, 20.3 seconds. So when we go into Excel here and graph this, we've got the RC experimental, which is just 1 over your slope, which is 5.828 seconds, and then you've got our estimated RC that we did earlier, which is 30 times 0.02 to give you 6 seconds. So then to check our accuracy, we can do experimental over estimated, and we get that we are 97% accurate in this experiment. So for the what if questions, what if you used a real battery to charge a real capacitor with no resistor in the circuit? The capacitor will take more time to charge and would not charge instantly. That's what would happen there. But if we use the actual ammeter instead of an ideal simulated ammeter, the current reading would be a good amount lower because of the resistance in the ammeter itself, whereas the one in our lab was simulated and everything was perfect and there was no resistance in it. So that's all I got for today. Y'all have a good one.